to part 2 of lecture for chapter 1. We're going to cover section 1.2 and 1.3, phases and classification of matter. Well, in chemistry and other sciences, but in chemistry, we study matter for the most part. So we're going to have to define what matter is, and then we're going to classify it. Matter is anything that has mass and occupies space. That's the definition for matter. It has mass, so anything, any object that has mass and occupies some space. Matter has two major classifications. One is pure substances and then mixtures. These in turn are divided into two groups apiece. Pure substances can be divided into elements, and we find these in the periodic table, or they can be divided into compounds that are not mixed with anything else. So compounds that are pure, they only contain that one particular type of compound. In a glass of water, for example, that liquid is only water if you don't add sugar to it. There's nothing else but water molecules in there, so it's considered a pure substance, even though we have a molecule or a compound instead of just a pure element, like hydrogen or oxygen, for example. So these are the pure substances. The mixtures, obviously just from the name, they are made up of two or more objects or molecules or compounds or atoms. We have homogeneous mixtures and heterogeneous mixtures. And the difference between these two is that in a homogeneous mixture, you cannot tell the parts from each other. You cannot, for example, brass is a mixture of copper and zinc. It's a homogeneous mixture because if I just look at a brass instrument like this one, I cannot tell, well, this is an atom of copper and this is an atom of zinc. I cannot really tell the difference because they are mixed very well at the atomic level. In a heterogeneous mixture, we can tell the different parts one from each other. If I have water and sand or water and pennies, for example, well, there's a difference between the two and I can tell them apart. I can tell which one is where's the water and where's the pennies. I can tell the two different parts of the mixture, therefore it's heterogeneous and not homogeneous. This is kind of a general overview of the classification of matter. We have pure substances and mixtures. Substances, then the pure ones are divided into elements and compounds, whereas mixtures can be homogeneous or heterogeneous. A pure substance, then, we'll take them in turn, is classified as that matter which has a fixed or definite composition. We can talk about a pure substance as an element or a compound. All the elements that are pure substances, obviously, they are found in the periodic table. So any element that you find in the periodic table, that is a pure substance. It is not mixed with anything else. It has a definite composition. In the case of the element, they're made up of, let's say, zinc or copper or iron. So they have a definite composition. A compound, on the other hand, that is pure, is always composed of two or more elements, the ones that we found up here, and they're always combined in the same proportion to each other. I have the example here of peroxide. This is peroxide, this is water. In peroxide, hydrogen and oxygen are combined in a 1-to-1 or 2-to-2 ratio. In water, however, I have a 2-to-1 ratio, so 2 hydrogens to 1 oxygen. In peroxide, I have 2 hydrogens to 2 oxygens, so 1-to-1 ratio. Here I have a 2-to-1 ratio. The important thing about compounds to remember is that if you change this proportion between the elements of a compound, then you change the compound, and here's the proof. If I I have 2-to-1 ratio here between hydrogen and oxygen, and if I change that to 2 hydrogens and 2 oxygens, so 1-to-1 ratio, I have a completely different compound than water. This is water, this is hydrogen peroxide. They are made of the same elements, but they're in different proportions, and that makes them different compounds. They have different characteristics, they have different physical characteristics and chemical characteristics, and so they are different compounds. It is important to remember that for a particular compound, the elements that make it up are always going to appear in the same proportion. And it doesn't matter if you are here or in China or in Germany or anywhere else in the world. Water is water. And what makes water water is that it's a mixture of a hydrogen and oxygen, and the ratio is always going to be 2 hydrogens to 1 oxygen, no matter where water is found. That's a characteristic of a compound and a pure substance. Mixtures, we said, are a type of matter that is made up of 2 or more substances that are physically mixed but not chemically combined. There is no chemical reaction that combines them. These 2 or more substances have different proportions, and we can separate them by using physical methods. Here's an example of that. When we boil pasta, we boil water and we add the pasta to it. That is, in the pot here, we would have a mixture of pasta and water, and they're physically mixed but not chemically combined with each other, and they can be separated by physical methods. We can put a colander and dump the contents of that pot out, and it separates the water from the pasta. And that way we use a physical method of separation, and we can separate the parts of the mixture. This is called a heterogeneous mixture because we can separate the parts very easily, and we can actually see the different parts instead of them being combined so well together that we cannot tell the pasta from the water. Homogeneous mixture, the composition is uniform throughout the sample. So the different parts of the mixture are not visible, and we talked about the brass where the copper and the zinc are so uniformly mixed together that we cannot tell where the copper is and where the zinc is. We just cannot tell them apart. In a heterogeneous mixture, the composition will vary from one part to the other. So if this up here is the liquid, down here is the solid, so there's a difference between these two from one part to the other. And the different parts of the mixture are visible. Whether I have pennies here, I can have sand, or etc., etc. That is because the parts of the mixture are not mixed very well together, and so I can tell the 2 parts from each other. This is the liquid water, and these are the copper pennies, for example. Those are the differences between homogeneous and heterogeneous mixtures. Now we also talk about states and properties of matter. We all should know this because we are very familiar with it. We've experienced it in our everyday life, that matter on Earth exists in these 3 physical states. There's a 4th, but we're not going to talk about that. These are very common. We have experienced, like I said, we've experienced it in everyday life. We have the solid phase, we have the liquid phase, and the gas phase. And different matter can undergo changes from a solid to a liquid, from a liquid to a gas, and back from gas to liquid, liquid to solid, depending on the temperature. Whether a compound then, whether we can find it as a liquid, solid, or gas, it will depend on these 2 things. The distance between the molecules that make up that particular compound, and the speed of the molecules, or in other terms, their kinetic energy, how fast the molecules are moving. In a solid, the distance between molecules is very, very small. As we move from solid to liquid to gas, the distance increases. The same is true for the speed of the molecules or their kinetic energy. In a solid, the molecules are very close together, very tightly packed. They don't have much room to move. As we move from solid to liquid to gas, the molecules in a gas are really far apart and they have a lot of kinetic energy. They move very fast. And therefore, their kinetic energy increases as we're going from a solid to a liquid to a gas. If we increase the kinetic energy, we also increase the speed of the molecules. This is a review, really, because we all know these characteristics. A solid has a definite shape and a definite volume. The particles in a solid are very close together and they're held by a very strong attractive force. It could be a covalent force, it could be an ionic force, and we'll talk about those types of forces later, but they're held very closely together by these attractive forces. And they're arranged in a rigid pattern. As you can see here, there's a pattern. And we can see them as crystals, for example. Once the particles are in this rigid pattern, they cannot move around. As you can see, they're very tightly packed, and so they cannot move very easily. They only vibrate a little bit in the fixed position. So if I have this silicon over here, it's already bound to oxygen on either side, and it cannot really move much because it will run into this oxygen or that oxygen. And therefore, it can only just vibrate a little bit about that particular position it has. This is true for all of these atoms. And therefore, the solid is very dense. In general, solids have high densities, and they are crystalline in form because these particles are very close together and they're arranged in a particular pattern to form a crystal. Liquids, they have a definite volume, but they don't have a definite shape. They are poured. They take the shape of the container they're in. This is a characteristic of a liquid that changes from a solid. They take the same shape as a container, whereas the solids do not. They have particles that move slowly in random directions. So these particles now are not as tightly arranged in a pattern as the solids. They're not rigid anymore, but they're in close proximity, not as close as a liquid, but they're close enough to feel the attraction or the interaction of the other molecules around them. Therefore, they move a little better, but they're not independent of the other molecules in that liquid. So they have a higher kinetic energy than the molecules in the solid shape or solid phase do, but they do not move as freely as the molecules in the gas phase. So if we think of liquids as the in-between phase, that would be correct. Gases, therefore, have an indefinite shape and indefinite volume. So it's not a defined shape or volume. They can take the shape and volume of any container that you put them in. It doesn't matter. So in the gases, the molecules are really, really far apart and they move at high speeds, which means from a couple of slides ago that they have very high kinetic energy. And because they have high kinetic energies, they don't feel attraction to other molecules. Because they're not very close to them, and they move at very high speeds, and therefore even if they were to interact with another molecule, they would interact so briefly because they're both moving so quickly that they would run past each other, so they wouldn't really have time to interact very much. And that's why gases have such a shape and volume that will fill any container. That's because their molecules are so far apart and they move at very high speeds, so they do not get attracted to other molecules in the gaseous phase per se. Now we can go from one phase to the other. So if we have a gas, we can go from gas to a liquid or liquid to a solid, and vice versa, all three of these, gas to a solid. And when we undergo that change, we call it a change of state because we're changing from one state of matter to another. And typically, when matter undergoes a change of state from one to the other, um, it does so at a constant temperature. So temperature doesn't change. For example, if we're melting, if we're going from a solid to a liquid, if we have ice, for example, and we're trying to melt it, during the melting phase, so when it's undergoing that phase change, we have ice at 0 degrees and liquid at 0 degrees. In the middle of that change, we have some of the solid that's melted, that's turned into liquid. So we have a mixture of a solid and liquid, and they both have the same temperature. At the end, when the solid has all melted into liquid, at that point, we will have liquid at 0 degrees Celsius, which is the temperature where the water turns into solid. So all the energy that we put into the system to try to melt it, it's not changing its temperature. All that it's doing is breaking those bonds that hold the molecules together in a solid to pull them apart a little bit, because the liquid molecules will have a little bit of higher speed as molecules, and they'll move a little freer. But to do that, it requires energy, and that's why there is no change in temperature when we change phase, because we're breaking those bonds between solid molecules to turn them into liquid, or whatever the state might be that you're changing. You could be liquid to a gas or gas to a solid, etc., etc. Melting and freezing. We know this very well. We know about melting and freezing. They're opposing processes. So for melting, we have to supply the heat give some heat to the solid to turn into liquid. Whereas if we're freezing, the liquid will give off heat, because liquids will have higher energy than solids. And so the liquid will give off that heat to turn into a solid. Whereas the solid, to melt it, we have to provide the heat to the solid to increase the energy of those molecules, the kinetic energy of the molecules in the solid, so that they will spread apart a little bit to become a liquid. These are called reversible processes. We basically, when call a melting point the point where the solid is changing to a liquid, and we call it freezing when the liquid is turning into the solid. That happens at the melting point or the freezing point, depending on which direction you're going. But it's the same temperature. Water, for example, has a freezing point of 0 degrees Celsius. Do not confuse this with Fahrenheit. It's 0 degrees Celsius, which is 32 Fahrenheit. But that's the freezing or melting point of water. It's the point in which either the solid, we add heat to the solid to become a liquid, or the liquid gives off heat to become a solid. So these are reversible processes. The only difference is that one absorbs the heat and the other releases it. Sublimation and deposition are two of the phase changes that we don't talk as much, or we're not as much familiar with. These happens when the matter goes directly from a solid to a gas, or from a gas to a solid. When sublimation occurs, so sublimation is the process in which the solid goes directly to a gas. When once again, this is a process that requires heat. The opposite process, where the gas goes directly into a solid, it's called deposition. And for this process, the gas gives off the heat. So these are reversible processes. This, we add the heat. To this, we remove the heat. Once again, there's no change in temperature anytime we go or the matter undergoes a physical change of state. There is no change in temperature. An example of this is dry ice. All of us have seen dry ice. What we see, though, is the solid dry ice, solid CO2, and then we see this mist or this vapor that has kind of an opaque color above the dry ice. And what that is gaseous CO2. And at the particular temperature and pressures that we have, room temperature and pressure, atmospheric pressure, the solid dry ice does not have enough pressure to actually convert to liquid first and then to gas. So it goes directly from solid to gas, and that's what we see when we see dry ice. These, pay attention to these because these are, like I said, we're not as familiar with these two phase changes as we are with melting and evaporating. Solid to gas directly is called sublimation, and gas to solid directly, it's called deposition. Think of depositing the gas molecules into a crystalline solid. That's why your deposition, you're depositing those molecules of the gas into the rigid array, crystal array of the solid. Then the last two phase changes that are reversible processes are vaporization and condensation. During these phase changes, we're taking either the liquid into a gas or the gas back to a liquid. For the liquid to become a gas, its molecules have to gain enough energy to escape the liquid surface and enter the gas phase, meaning their kinetic energy has to increase. And for the gaseous phase, the molecules have to give up some of that kinetic energy to turn into a liquid. When the liquid goes into a gas, turns into a gas, we call that vaporization, and we have to supply heat. The opposite is true. When the gas converts into a liquid, it gives off heat, and we call that process condensation. These are reversible processes in which one has to, for liquid to gas, it has to gain heat, and gas to liquid, it gives off the heat. These are the 6 different processes that we will talk about for the phase changes. Now, physical and chemical properties or physical and chemical changes. These go along with some of the phase changes that we were talking about, at least the physical part. Now let's talk about physical properties. These are properties of matter that are observed without changing the identity of a substance. It remains the same. Some of these properties include, we'll talk about the shape, the physical state, boiling, freezing, or melting points, the density of the particular object, the color, or any other characteristics that can be observed without changing the substance. Here's an example. If I showed you this picture, you would instantly look at these and say, oh, this is copper. Why? First of all, because it has this reddish color, this reddish orange color, and it will distinguish it from another type of, from aluminum pans, for example, because aluminum doesn't have that reddish color. So we say, okay, this is copper. It's reddish orange in nature. It's shiny. That goes for all metal. Metals in general are very good conductors of heat and electricity. If we were to look at this at different temperatures, we'd say, well, at room temperature, which is about 25 degrees, it's a solid. And here's the melting points and boiling points, extremely high melting and boiling points, but they're there. So if we looked at a mixture of all of these characteristics, we'd say these are physical characteristics of copper, of the metal copper. Now, a different metal will have slightly different properties. They may not, we already mentioned aluminum. Aluminum, it doesn't have this color, but it's still it's solid at 25 degrees, and it's a good conductor of heat and electricity. It can be shiny. The melting and boiling points, however, would be different because it's a different metal, so it's got a slightly different physical property than copper does. Physical changes are associated with physical properties. So physical changes occur when the matter undergoes just a physical change of state, but we do not change the composition of that particular compound. And remember, we said that if we change the composition, that means we're changing the identity of the substance. And in this case, when anything physical, to measure physical properties or a physical change, we do not change the composition of a molecule or a compound. For example, water exists as ice, water, liquid, and steam. So if I change from one to the other, I may change the appearance of a substance, but I do not change the composition. It's still water, whether it is ice, liquid, or gaseous form. Now, a physical change can alter the physical appearance of the substance and doesn't mean that the composition has changed. For example, when I dissolve salt in water, the crystals will, so the physical appearance of salt will change because the crystals will dissolve and they're not visible anymore. So the physical characteristics or appearance of salt is going to change. But they can be reformed if I allow the water to evaporate. So I have not changed the composition. It's still there. It's just changed the appearance a little bit. And so it's a physical change and not a chemical change. The chemical properties and changes are slightly different. Chemical properties, they describe the ability of a particular compound to interact with other substances or change into a different substance. How well they react, how they react in general, what they produce, etc., etc. That's a chemical property of a particular compound. When matter undergoes chemical change, we have a new substance that forms. It is different from the original compound that it started. This new substance will have a new composition. It'll have new physical properties, new chemical properties. It will not be the same as what you started with. Here's an example. When we take a dessert, and I think it's creme brulee, and you pour a little bit of sugar on top, and what you do is you light a blowtorch on fire and you caramelize the sugar at high temperature. You're making caramel out of it. This is an example of chemical change. What you have here is not sugar crystals anymore, and it's not even melted sugar. You've caramelized it. You have changed the structure of the original compound, which was sugar. Now it has a new composition, and it will have new physical and new chemical properties because every compound has different chemical and physical properties. And if you start with sugar but end up with caramel, that means that you have changed the composition and the physical and chemical properties of sugar to fit a different compound. And you cannot go back from that compound to sugar like you would if you dissolved sugar in water, for example, and just allowed the water to evaporate. You can allow this to evaporate all you want. It's not going to change back to sugar because it is a new substance. It underwent a chemical change, and now it will have a new composition and new physical and chemical properties. That is very important. Now let's take a look at this problem and just check whether we understand physical or chemical changes. Ice melts in the sun. So if I have ice melting in the sun, is that a physical change or a chemical change? If you answered a physical change, you are correct. because all I'm doing is melting. The ice is undergoing a phase change. It's melting into liquid ice, but it's not really changing into a different compound. Therefore, it's a physical change and not a chemical change. Copper is a shiny metal. This is a physical characteristic. Remember, we talked about that a few slides ago. I am not changing copper into a different compound, so it is a physical change or a physical characteristic. Paper can burn. This is a chemical change. Anytime you burn anything will be a chemical change, because when we burn paper, we all know that it doesn't remain as paper anymore. You change it into something different, into different compounds. And therefore, it will undergo a chemical change, or it's a chemical property of paper to say that paper can burn. A silver knife can tarnish. Now, many of us are not familiar with this language because we don't use pure silverware, although the name is there, silverware. They were made of silver, but not anymore. And in the old days, in the families that were rich enough to have true silverware, they would tarnish. They would see that they were tarnished, and they would have their servants polish the silverware to a high gleam. Well, what happens is, with all metals, if they're exposed to air, they tarnish, or we call it, they react with the oxygen in the air to form an oxide, a different compound. Therefore, it undergoes a chemical change. Silver would react with the oxygen in the air to form silver oxide, silver 1 oxide, and therefore the tarnish part of it tells us that it's a chemical change because it is changing into a different compound. It's not silver anymore. It gets this dull look to it, whereas silver is shiny. Therefore, it's not just a physical change, it's a chemical change. It's now changing into a different compound. What if I have a magnet that removes iron particles from a mixture? If you answered that as a physical change, then you are correct, because a magnet does not do anything to the iron particles. They still remain iron particles. They just separate them from a mixture, because iron is magnetic and other metals are not. Or you can have iron and sand. Whatever the case might be, the iron can be removed by using a magnet, because we know that iron is magnetic, whereas other types of compounds aren't. So it's a physical separation, a physical change of iron from a different compound in a mixture, and I can use a magnet to separate the two. So it is a physical change because my iron is not changing to a different compound. It's just being separated physically from another compound in the mixture. Okay, this is the end of the part 2 of the lecture for chapter 1, and then we will talk about measurements and units in the next section.